Welcome everybody. So this is ECO719 Mathematical Economics. And today we're gonna start working on continuous dynamical systems, continuous time dynamical systems. This material is directly from your textbook, Takayama. I believe chapters 6 and 7. But I will be going back and forth between different chapters because I have so there's a large material in those chapters. So I don't want to cover all of this. I just want to cover some essential parts that you need. So of course you don't see my screen right now. Let me just share it. Okay. So let me put this over here. Okay, so this is continuous time dynamical systems. Okay. Now, obviously, we have to define time, right, before we start. So I will denote time by t, as is usual. In most of the resources, in continuous time, time variant variables are denoted in this way. All right, so time t in parentheses. But for notational sake, I'm going to use this. All right. So usually this is for continuous time systems. This is for discrete time systems. Okay. But I will use this as well for continuous time. And when we talk about time and time variant variables, we are actually working on something like this. So if time is continuous, history will be a subset of the real line. Okay, so H will be history, and time will be an element of history. So here, time, of course, passes by instants, right? For this reason, there is no hole in the set H because there is no hole in the real number system, right? Now, this H could be defined in various ways. More generally, if you take it as the real line, it is basically this, right? But most of the time, we want to be very specific about the initial point, okay? And sometimes we want to work with models where there is a particular terminal date. So this is then, so these are infinite horizon models, right? Infinite horizon. And here we have finite horizon. Okay. So when I talk about a variable changing in time, I basically talk about a function actually, right? So x, whatever variable that is, it is a function of time. So it takes, the argument takes values from the history, right? For each historical instant, there is a value associated with that variable, and usually we talk about real valued variables. Of course, in econ, we have usually real valued variables, right? Now, when we start continuous time dynamical system, we will be, of course, thinking about more than one variable, right? So we have x1t, x2t, dot, dot, dot. So when I write xt, most of the time I will be referring to x1t, x2t, dot, 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 x and t, right? So the main problem is this. Most of the time, we do not know this function. Okay? Most of the time, we do not know this function, but what we know is usually this. Okay? So usually, we know this, and this would be, for instance, a function of all the variables in the system. Okay, and this could be for all I. Now, for this thing, we have a particular notation. Most of you, I guess, remember that. We use a dot over the variable. Okay. So what this means is that instantaneous change in variable xi. Okay. Now, this equation tells me that this instantaneous change in variable xi will depend, in general, in a nonlinear way, to all the other variables. And sometimes this function is not stationary. Okay, so it depends on x values. Okay, and also it depends on time itself. So this can also be true. In that class, we're going to be dealing with mostly the stationary case. Okay, so it will not, so f function or f functions more generally, because we have more than one variable here, f functions will not depend on t. Okay. Now again, we don't have this, but we have this. So we want to use this knowledge to understand the behavior of this function. Okay. Behavior of this function. That's the main task here. Now let's take an example. Okay. Now this is Solow's model. Very famous, right? So you have capital stock per worker. All right. Now this changes in time through two forces. There is a saving rate, and there is a production function. And let's say there is population growth and so the labor force growth basically, and there is depreciation, right? So S and delta is between 0 and 1, N is greater than 0. All right, and alpha, of course, as well, between 0 and 1. So what do you see here is that this tells me in per worker terms, there's production per worker. That translates into income. A fixed proportion of that income is saved. This becomes investment per worker, right? Then again, at per worker levels, we have depreciation. One part is because of depreciation. The other part is because of population growth or labor force growth. Okay? So then this is the law of motion for KT, right? Now, as you see, I do not know KT as a function of time, right? I do not know that. What I know is the instantaneous change. I mean, what I know is how the instantaneous change in capital stock per worker is determined by the model parameters and the capital stock per worker itself. All right? Now, what can I do with this equation? First of all, of course, this is a differential equation, right? There's a special name for this. Differential equation. Usually, when you see x dot t and xt within the same equation, so if you have something like this, then we are talking about a differential equation. Now, in this case, this is a nonlinear differential equation, right? It is nonlinear because of this, and it is first order. Why first order? Because we have the first order derivative of kt with respect to t. Okay. So then the question is, what can I do with this equation, right? What can I do with that equation? As you see, I can write the production function in a more general way. In the simple Cobb-Douglas case, this would be kt alpha. Well, you can do several stuff. You can actually solve this. There's a nice way of solving this through Bernoulli equations and the change of variables. Okay, the idea basically is to make this a linear. I mean, transform this itself, transform this thing into a linear differential equation by a change of variables. Then you can solve it. So this is you know, what you learn in your undergrad lectures. We can create a different example. Imagine an ISLM model, but now it will be a dynamic ISLM model. All right. So how can we imagine this? Well, in the ISLM model, there are two endogenous variables, right? Output and interest rate. So you may imagine output will grow if expenditure, so this is positive, so this is the expenditure function. Okay, if expenditure is greater than output, right? So this is something like that. And interest rate would be growing, right? If liquidity is larger than, let's say, money supply, right? So this is output. This is liquidity function or money demand. And this is money supply, right? So now what you see here is that these are, of course, time variable, I mean, time variant things. Mu is fixed and beta is positive. So now, as you see, instead of just drawing LM and IS curves, right, and defining an equilibrium, we are now interested in the dynamic behavior of these variables when these are steady state characterizations. Okay, when you equate expenditure to output, you basically have the IS equation. When you equate liquidity to money supply, you're going to have LM equation. All right. Let me give you another example. So you may imagine a static general equilibrium model. So suppose that there are n goods in the economy. Okay. And then, of course, then there's this price vector, right? P1 ... Pn. For now, suppose that these prices are strictly positive, right? So we're interested in positive prices. So how do we, and also let's define excess demand functions. Okay, so excess demand functions are, let's say, FIs, okay? As you see, the excess demand function at any good depends on all prices, right? Because most possibly these commodities are substitutes or complements. So how do you define the Walrasian equilibrium? Well, the Walras in general equilibrium requires for each I excess demand to be equal to 0, right? So there will be a P star, which is the equilibrium price vector. And that equilibrium price vector makes excess demand equal to 0 in each market. Then this would be your Walrasian equilibrium. And then you can study the stability of the Walrasian equilibrium by studying this. Making all variables depend on time, price in a market would be increasing if excess demand is positive. Okay. Now again, depending on the excess demand functions, this is a nonlinear dynamical system. All right. There could be many other examples that are useful. So if you let me give you one final example. So you may imagine a wealth accumulation problem. Okay, so suppose that you have your consumption, and then you have the increase in your wealth stock. Now that would be depending on the interest rate and the wealth stock in instant t, right? So then, of course, in this model, you have to say something about consumption. Now, just imagine that this is so you may imagine that the increasing consumption would depend generally on what you have as your wealth and what you have as your consumption. Okay. Again, this is a nonlinear, in general, nonlinear consumption wealth model. Okay. In all of these models, we would be, of course, interested in the initial values. Okay. In the ISLM model, we want to know where do we start. In the wealth model, we want to know where do we start. In the general equilibrium model, again, we want to know where to start. Okay, and sometimes we would also have terminal values. Okay, terminal values. Oh, okay, we also have the capital stock variable, right? So sometimes we want to have, or we have for I mean, depending on the nature of the problem you are studying, depending on the nature of the model you are constructing, you may have the end values as well. Okay. And of course, these would be important in finding the definite solutions. Okay. Now, after giving these to you, let me just stop here if you have any questions. So I'm showing you basically this. There is this time concept, which is somewhat abstract, okay, but it passes by instants. So there's a continuous time here, and we define variables that change in time. So for each instant, they can take different values. The problem is that I do not know that function. I do not know that xt function that maps time to the values of x. Okay, if I knew that, if I knew that function, then there's no problem, right? I already know what each variable takes, what value each variable takes at any particular t. I go home. There's no problem to study, right? But most of the time, in the economic models, in the dynamic economic models, we know something about the law of motion. Okay, I know, for instance, in the wealth problem, if I spend some portion of my wealth to consumption, another portion goes to my saving. All right, I know that if I have the production level, which depends on KT in the Solow model, right? So KT alpha becomes the production and then income, and then investment per worker becomes S times KT to the alpha. Then I also know some constant fraction of this capital stock will depreciate and will be diluted because of labor force growth. Then I understand how much it changes. But I do not still exactly know what the function is. Right? Same is true for ISLM models. Same is true for any dynamic model that you basically define by laws of motion. All right. Now the question becomes this: okay, I have time, which is continuous. Then I have some variables that change in time, and then I also have how they change. I also know how they change. The question is what to do with this. Right? What to do with all this? And that answer is somewhat interesting, because most of the time we do not particularly interested in finding this function. We are not extremely obsessed for solving the model, okay? Solving for the time path, okay? If we are interested in solving for the time path, usually we use computer for that. Okay, usually we do it numerically. For instance, you can very simply find the Solow models. For instance, I mean the time path of capital stock for 0 to positive infinity. All right, if you can do it in you can even do it in Excel, but there's an analytical solution for the Solow model. For some models, there is no analytical solution, so you have to use computers. What we do with these dynamical systems, now let me write a general form. Okay. So here F is basically defined from a subset of Rn to Rn, right? Because I have a law of motion for each variable. Okay, so if you want to write this explicitly, you have x1t dot f1 x1t x2t dot 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 xnt. You have x2t dot f2 x1t x2t dot dot dot, and that goes on. Finally, you have xnt dot equals fn x1t x2t dot 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 xnt. Okay, so this is the shorthand notation for all this. All right. Now, what to do with this? Well, we're gonna do three things. First, existence of a steady state. Okay. Second, uniqueness of a steady state. And third, stability of steady states. Okay, these are the three things that we focus, because again, if I want to solve this, if I want to know xt as a function of time, if the system is sufficiently nonlinear, then I use a computer for that. All right? But without using a computer, we can still do something very important. Okay? We can still analyze this system by analyzing the existence of a steady state, the uniqueness of a steady state, and the stability of this steady state, or the stability of different steady states. Okay? So, again, let me write the system here. An initial point is given, okay? And f is a function defined in this way. Okay. Now, steady state. And by the way, you realize that I'm not using this version, right? In general, there's dependence on t, but I'm working with a stationary version. Now, how do you define the steady state? Very simple. X star in X is a steady state if f of X star equals 0. Okay, and 0 here is of course the vector, right? It has n dimensions. So that's it. That's the definition of the steady state. Then you can of course define the set of steady states. Okay, remember a set is defined by two things. First, a typical element. A typical element will be this, and then a property for this typical element to satisfy, and that property is that. Or if you want to write it more, I mean, you can write it more specifically as fi x star equals 0 for all I. Okay, so these two statements are identical. This and this are identical. Okay, for instance, if you look at the Solos model, right? So you have S kt alpha minus m plus delta kt. So a steady state would be this, right? K star to the alpha equals m plus delta k star. So k star would be what? S divided by m plus delta 1 over 1 minus alpha, right? In the ISLM model, you have the IS equation, right? IS equation is EYR equals Y, and you have the LM equation where liquidity equals minus supply. So you see you have a 2x2 system which is nonlinear, but if you solve this, that solution is exactly there. Okay, so this is LM, in other words, R dot equals 0, so the money market is in equilibrium. This is IS, Y dot equals 0, so the goods market is in equilibrium, so you have Y star, you have R star. Okay, then you have the wealth problem, right? W dot equals RW, and you have C dot T equals F WT CT, right? So what do you have here? W dot equals 0 means you have C star equals R W star. Then C dot equals 0 implies F C star W star is equal to 0. Then if you replace C star, you have F R W star equals 0. So depending on F, you solve for W star, and you solve for C star as R W star. Right? The other example, yeah, the other example was the general equilibrium model. So P dot T equals FPT again. So there is a model is in equilibrium if all markets clear, right? So I mean, the condition, the definition of the model is in equilibrium is that all markets clear. Okay. So that's the steady state. Let me now stop here for the last 2.5 minutes for your questions. Otherwise, we're gonna take a break and continue with the you know, uniqueness issue and stability issue. Then I will show you some further stuff, of course, because as you see, nonlinearity will limit what we can do. So we're gonna linearize these models, okay? Because of course there's a trade-off there, because when we linearize the model, we must be close to the steady state, right? So there are different research questions that we use in our research. Depending on our question, we do different stuff. So I will show you both. I will show you the nonlinear versions. I will show you the linearized versions. Any questions, comments? Nothing? Sıla orada mısın Sıla? Dinliyor musun bu dersinde?
Dinliyorum hocam, buradayım.
Tamam, biliyorum dinlediğini de bir selam
Kontrol
göndereyim.
etmek istedim.
Kontrol ettim. Twitter'a yorum yazdım diye beni linç ettiler.
Ne için hocam?
Öğrencilerim derse katılmıyor, çok şikayetçiyim diye yorum yaptım.
Çok haklısınız.
Neyse, yani sizi kastetmedim orada ben. Lisans öğrencilerinden daha çok şikayetçiyim de. Siz neredeyse tam kadro derse katılıyorsunuz. Bir de bu materyal, tabii şöyle bir durum var. Biraz üstüne çalıştıkça şey ortaya çıkacak. Yani biraz çalışın. Yani kitapta bir sürü sorular var. Bir sürü başka kaynaklarda sorular var. Biraz bunları düşünüp çalışmanız lazım. Tamam, şimdi 1 dakikadan az zaman kaldı. Benim saatim 1:38. Muhtemelen bir 15 dakika falan tutacak bunun şeyi. 55'te buluşalım, olur mu?
Tamam hocam.
Tamam hocam.
Tamam hocam.
Okay. Okay, bye bye.